let's start this up. So I know it feels extra early today. I don't know why, but for me it does. I'm like, I think because I got here earlier than usual. I don't know. I don't know how that works. One, two. Yes, I only have one set left here. We can share. Thanks. Okay. Yes. So, I handed out assignment 5. A little bit longer. Not terribly long, I don't think. It's essentially like a practice test. So it has all the types that we'll be covering in chapter 5. Of course, last day we only started on one sample mean sigma unknown, right? And then today we're going to move into matched pairs or paired data. And then there's also going to be 2 samples, 2 independent samples on here. So as we go through, you'll be able to do more of the questions. But that's why I wanted to get it to you a little bit earlier, because it's not due until the 18th, which I think is I know is the same day as our test. So essentially a practice test, get you ready. Okay. So let me see here. So last day we spent a lot of time talking about what's the t distribution, how do we use the t-table to find p-values and critical values, right? Everything that you could possibly want to know are in those in that chapter 5 bundle of notes. And I ran out of notes. So if you need some, you can grab some after class. I'll have to print them off though, somehow. Okay. Oh, and for your assignment 4s, I definitely meant to have them done. I flew too close to the sun. Didn't quite get them finished this morning, so oh well, I'll post the solutions. And once your marks are up on Moodle, you can stop by my office if you want to come grab them. Otherwise, I'll bring them to class on Monday. Cool. All right. So let's keep going on this example that we were working on last day. So today we're gonna finish this example, and then we're gonna talk about, well, what do confidence intervals look like in a one sample mean sigma unknown situation. They're not gonna look that different from the sigma known situation, so we'll kind of fly through that, and then we'll get into paired data. So Summit Projects, we've seen this example, but it's a full service interactive agency, blah, 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 blah. So they did a redesign, and before the redesign, their average sales were $24.85. And then after the redesign, the analyst selects a random sample of 58 sales and finds the mean to be 2605 with a standard deviation of 1020. Okay. So all this information is from your sample, right? Specifically, the standard deviation is just calculated from your sample, right? And so that's why we have sigma unknown, right? Because we're just using our sample standard deviation. So, you guys can grab assignment 5. So we went through and we said, okay, well, our hypothesis our null hypothesis is that the mean sales are 24.85, the same as before the redesign. Right? Now, what we suspect, or what we're probably hoping, if we're analyzing this, if we did a redesign, we're probably hoping for higher sales, right? And so we're hoping to show that mu is actually greater than 24.85. Because we only care about one of the extremes, right? We have a one-sided test. So whether your test is one-sided or two-sided comes from the sign in here. Right? Only if you have a not equal to in here, if you just want to show that they're different, then you have a two-sided test. Then we went through and step 2, we did the test, right? We calculated our t, and we found a t of 0.896. Right? That's not very far from the hypothesized mean, right? 0.896 standard errors from the hypothesized mean. We're already suspecting that we're not going to be able to reject the null hypothesis, right? Because we can only reject the null hypothesis if we're far enough away from the hypothesized mean. And remember, t has to have at least 3 decimal places, right? It can have more, but at least 3 to be able to use the table properly. Okay. And then we started on step 3. I'll pretend we started fresh here. March 6th. Even though we didn't really. For finding the p-value, right, we have to use the t-table. P's and t's and alphas abound. So what we said was, okay, we take our calculated t. For the t-table, we have to find our degrees of freedom. Right? Oh, I better remember what they were. Which I show the calculation, right? 58 minus 1 is 57. So we have 57 degrees of freedom. So we can go to our t-table, or was it here? And say, okay, well, starting from the top here, we've got our degrees of freedom line, column, right over here. And so we go and we try to find 57 degrees of freedom. But once we get down here, we see our options are either 50 or 60, right? The rule is that we have to round down to 50, right? Because if we go to 60, we're saying we have a sample size of 61, which we don't have, right? It's better to say that you have a smaller sample size than you actually do, right? And so that's why we have to go to 50 degrees of freedom. And so that's what I make a note of in my notes, right? Degrees of freedom is 57, but using 50. Okay. And then I take my calculated t, which was the 0.896. Was it 0.896? Yeah, thank you. And I just kind of grab it from step 2. And then now I try to figure out where it would fall. I don't have to go very far for this one, right? Where it would fall on this line. So once you've picked your degrees of freedom, you can't stray, you don't look at any other lines, just the 50 degrees of freedom. And you see that your calculated t falls between 0.849 and 1.047. So you jot those down. Oh, hard because you can't have 2 things open at once. So in the center, I start in the center and I write out my calculated t in absolute value, brackets, I guess, just straight vertical lines around it, which just says if you have a negative value, you just drop it, right? Because the table only has positive values. Okay. So we found that our t, our calculated t, is between 0.849 and 1.047. So now we use those values. Now we can kind of scroll down, I guess, to the bottom of the page where we can choose between the one-sided P or the two-sided P. This is where we have to go back to our hypothesis and say, okay, did we have a one-sided or a two-sided test? We had a one-sided test, we said. So in the center, again, I'm going to say my one-sided p-value is between two values. Notice that I just start with my less than, and then I use less than again. So I don't change the symbols or the inequalities. Okay. So what we find here is that, okay, we're between these two values, so 0.849 and 1.047. And so if we roll down to the one-sided P, right, we see that our one-sided P is somewhere between 0.15 and 0.2. The important part is because of the way we've set up our symbols, right, we have to read from right to left because this one's smaller than this one, right? And so that's the only kind of switcheroo that we have to do. But as long as you keep that in mind, you're okay. So our one-sided p-values between 0.15 and 0.20. Yeah. All of this that's on the screen here has to be included for full marks for finding the p-value. You have to tell me what your degrees of freedom are, what you're using, where your t is on the t-table, and also what your p-value is, of course, or where your p-value might be. Okay. But now we know our p-value is somewhere between 0.15 and 0.2. Okay. So step 4 is our conclusion. Has to have 3 parts, right? First step is we take our p-value and we compare it to our alpha level, right? Is it less than or is it greater than the alpha level? I don't think it said an alpha level. It didn't give us an alpha level to use. So the default is 0.05, right? So since our one-sided p-value is between 0.15 and 0.20, it is not less than our assumed alpha level. It is not less than our assumed alpha level. Of 0.05. If it's not less than our alpha level, right, then we haven't moved far enough away from the hypothesized mean to reject it, right? So really what that's saying is, which means we do not have enough evidence, to reject H0. Remember, your conclusion is always in terms of, can you reject H0 or can you not reject H0, right? Because we've done all our testing assuming the null hypothesis is true, and so the alternative doesn't really come into play until you've rejected H0. Then you should probably say what you've rejected it in favor of. Okay. So here's your first 2 parts of your conclusion, right? How does the alpha level, or how does the p-value compare to your alpha level? And then what does that mean in terms of the null hypothesis? And then finally, the forgotten step, what does that mean in terms of the question, right? That means that the average sales have not increased significantly since the redesign. Therefore, the average sales have not increased significantly since the redesign. Redesign. Probably not good news for the consultant, but that's just what the data is telling us. Any questions about that one? So now we've done 2 examples together of hypothesis testing for one sample mean, sigma unknown. Oh, one note about assignment 5. Which question was it? Oh yeah, question 3. It's from chapter 4 where you have to find a sample size, but I kept it on there because, well, 1, I didn't do it on assignment 4, and 2, because it's about platypuses and goes with the theme of the assignment. It's actually an old test that I had, but now it's been demoted to an assignment. So lots of fun facts about platypuses. And yes, the plural is platypuses. Cute, right? So let's move on to confidence intervals. Right, we've already seen the comparison between confidence intervals for sigma known versus sigma unknown. Right, the only thing that's changing is our S instead of sigma, right, our sample standard deviation. And now we're getting a T star instead of our Z star. Right? So, but we know how to find our Z star, and we talked about last day how to find our T star. We do the same thing, right? We go to the T table, find our confidence level, and then just stop at the line where we find our degrees of freedom, right? And that's how you're going to find your T star. So of course I've got a little list here, right? Your degrees of freedom in this situation is n-1. X bar is the sample mean still. T star is the critical value down in the T table. T star is the only thing that determines the confidence level, right? How confident are you? Okay. And so, and then S over root n is the standard error of X bar, and this whole plus minus chunk is still the margin of error. And so same terminology applies, just slightly different values. So we'll go through this example. Business bankruptcies in Canada are monitored by the blah, 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 blah. A study is based on a random sample of 75 reports from the current year. The average debt, liabilities minus assets, doesn't matter, is, so the average debt is 92,172 with a standard deviation of 111,538. Construct a 95% confidence interval for the average debt of these companies at the time of filing. Great. We have a sample mean. We have a sample standard deviation. And so here, let's just go through and highlight. So we've got, here's our N. This is from our sample, making it X bar. And here, it's our sample standard deviation. Therefore, sigma is unknown, right? Because we're just given the sample standard deviation. Of course, because we're working in the sigma unknown section, right, it's obvious, right? But when in the test, when you've got choices between sigma known and sigma unknown, right, that's where it gets a little difficult. Oh, and while I'm thinking about it, on Moodle, I posted extra practice problems, assignment 5. They used to be part of assignment 5, and it's just a long list of different questions which you have to read and figure out what type they are. So it's not for marks. I posted the solutions, but it's really good to just read a ton of questions. You don't have to do them. You can. but just read them and try to figure out what type of question each of them are, right? And so for those assignment 5 extra practice problems, there's only chapter 5 ones. But on the practice test, there'll be others. Okay, so we're given, like I said, we're given n, we're given x bar, we're given the sample standard deviation. And again, in the box is everything that you need to have for full marks on a test or on an assignment. Right? So nothing in the box is optional. Everything has to be in there. And that's what I did, or that's what I've done throughout the chapter 5 notes. Just highlighted everything that you need to have, because it's a lot of stuff, and for some reason people think it's way too much stuff, and surely not all of it is mandatory. It is, actually. But in the beginning, you're just telling me how you found your T star, right? So using the T table with n-1 degrees of freedom, so we have a sample size of 75, so we have 74 degrees of freedom. When we go to our table, right, we're finding, okay, well, 74, my options are 60 or 80. Of course, I have to round down to 60 degrees of freedom. And if I'm doing that, I'm going to make a note of it, right? So, but using 60 degrees of freedom. And I'll go to my tables here. Right, so here we were trying to decide, okay, 74 degrees of freedom, somewhere between 60 and 80, I have to go to 60. 80 would be saying I have a larger sample size than I actually do. And then, I keep forgetting I can bring this around. I don't know if I'm talented enough. We wanted a 95% confidence interval, I think, right? Yeah. So then we start up here at 95%, and then we scroll down, but only until we hit 60 degrees of freedom. Oh, how convenient. 2.000. Nice. Which kind of goes with really goes with our 68, 95, 99.7 rule, right? So that's still holding true. So our T star is 2.000. And so then we can just plug in our values and calculate our, I start by calculating our standard error, right? And then I multiply it by 2. Because you're multiplying and dividing, the order doesn't matter. And then make sure you keep all your decimal places until the very end, right? And whenever you're dealing with money, it's easy. Then you know you have to just round to 2 decimal places, right? And so here we're dealing with money, so I don't even have to tell you how many decimal places, right? But you have to keep all your decimal places throughout until the very end. And so our interval, lots of commas in here, mostly because it gets too long if you don't break it out. Our interval is between 66,000 and 117,000. So whenever we've done a confidence interval, we have to interpret it. And we use that blurb, so we're 95% confident the interval from 66 whatever to 117 whatever captures the average debt of these companies at the time of filing. This here, this blurb captures, what's it capturing? You just steal that from the question, right? I asked you to make a 95% confidence interval for the average debt of these companies at the time of filing. So you can just take that little blurb and put it in your interpretation. So it's not something that I kind of came up with. I'm just kind of regurgitating the question as an answer. Any questions about that one? Okay. So let's do one together. Do I have any side notes here? No. Oh, this one's kind of weird, but whatever. So a manufacturer of high resolution video terminals must control the tension of the mesh of fine wires that lies behind the surface of the viewing screen. I mean, people have come up with these questions. It's like so detailed. The tension is measured by an electrical device with output readings in millivolts. A random sample of 20 screens has a mean of 306.32 and a standard deviation of 36.21. You have a 90% confidence interval for the true mean tension mu of all the video terminals produced this day. I think there's 3 mentions of the population mean, right? The true mean is the population mean, mu is the population mean, and of all the video terminals that day is also the population mean, right? So I've kind of redundant, because there's 2 redundancies. Does it make it redundant? Anyways. But just to emphasize that our interval is hoping to talk about the population mean. All right, so I'll use the whole page here. Make a note on the side what we're given. We're given N is 20 screens, and that sample of 20 screens has a mean of 306.32 and a standard deviation of 36.21. Because we only have the sample standard deviation, therefore sigma is unknown. So I usually start by writing out the formula that I need. So x bar plus minus t star times s over root n. And then I just check to make sure that I have all the components that I need. I have x bar, I have s, and I have n. The only thing I need is my t star. And so I'm just going to write out how I'm going to find it. So using the t table with degrees of freedom equal to n minus 1 is 20 minus 1 is 19. We find T star is, let's see here. So we have 19 degrees of freedom. Oh, I forgot to remember. A 90% confidence interval. A 90% confidence interval. We have 19 degrees of freedom on our table, right? So we're just going to use that. And 90% here, I'm landing on 1.729, but it's actually kind of hard to see here. You guys getting 1.729? Cool. So then our T star is 1.729. 1.729 for a 90% confidence level. Oh. So now, now I can go ahead, x bar plus minus t star times s over root n. Now I can plug in all my values, right? And so we had x bar was 306.32 plus minus t star, which we just found was 1.729, times s, which is 36.21, bless you, divided by the square root of 20. Let's see if I can. 36.21 divided by the square root of 20. Keeping the 1.729 out of it for a little bit longer, times 8.096802.147. You can skip straight from plugging in your values to just calculating the margin of error if you want. That's fine. I'm just showing it so that you can check your work. But then times that by 1.729, I get plus minus 13.9993791, 306.32. So our margin of error, right, is 13.9993791. So I'm going to store that so I can use it. And then I have to find 306.32 minus the margin of error. And how we write it, right, you find your lower bound and then your upper bound separated by commas enclosed in round brackets. So 292.320629.1 up to 306.32 plus the margin of error, 320.3193709. Here, we're not dealing with money, so it's not obvious how many decimal places, but because I gave the mean and the standard deviation to 2 decimal places, I'm just going to round it to 2 decimal places. Seems reasonable. So, or 292.32 up to 320.32. I guess I better add a page here. Almost didn't need it. So once we've done our confidence interval, right, we have to interpret this interval. And so we use the same blurb. We are 90% confident the interval from 292.32 to 320.32. You can throw in units if you want, but I'm not going to. Captures the, and here's my ultimate redundancy, the true mean tension mu of all the video terminals produced this day. Let's see if I can remember that. The true mean tension mu for all video terminals produced this day. How would I do? Of not 4. Oh well, pretty good. So not different from the sigma known situation. It's just determining which formula to use, and then everything stays the same. Any questions about that one? No? Okay. So, are you ready for another type of question? Don't say no. You have to be. So, so like I said, so far we've seen one sample mean sigma known, and then now we just covered one sample mean sigma unknown, right? We know how to make confidence intervals and do hypothesis testing for each of those, right? Now, we're gonna start talking about paired samples, okay? This is the first time that we're gonna start to have two samples, right? But it's a special case where these two samples are matched up on one individual, right? And so a special case where you have two observations on the same subject or individual, right? Thinking of things like a before and after study, right? And so you write a test before, you get a score, and then you write a test after some training, and then you get another score, right? If you did really well in the beginning, right, even if you improve, right, your score was high to begin with, but then it's going to be probably even higher after the training, right? And so paired samples let us do comparisons, kind of how did each individual improve or decrease, depending on what you're talking about, right? So I've got some examples out here, but really they're all the same pre-post. So before and after, thinking about yourselves, right? You're going to write a test 1, you get a grade on test 1, and then you're going to write test 2, get a grade on test 2. If I want to see if there's been an increase in your grade, right? If you've all improved as a group, then I would take the difference between the grade on test 1 and the grade on test 2 and analyze that difference. Okay? And so that's the trick that we use for paired data. And it only works because we've got these paired observations on each individual, right? So technically, yes, we have 2 samples now instead of just 1, right? But because of how the data has been collected, we calculate the differences. So we make a new column of the differences between sample 1 and sample 2. And then we just analyze those differences as if they were one sample, right? And so that brings us back to the hypothesis testing scenario and the confidence interval that we just did in the previous section, right? And so that brings us back to a one sample mean sigma unknown, but the special case where we're talking about one sample of differences instead of just whatever we want. So I've got that list here. Let's see if I forgot anything. So I use matched pairs, paired data interchangeably. Sometimes I like to say matched pairs. Sometimes I say paired data. Of course, if it's got the word pair in there, you know what I'm talking about. As long as we do our subtraction in a consistent order, it doesn't matter which one we subtract from which, right? Which sample is being subtracted from which. So let's talk about kind of the ins and outs of hypothesis testing before we do an example of it. So what's nice is once you've decided that you have paired data or matched pairs, this is your null and alternative hypothesis. The only thing that could change is the sign in the alternative hypothesis. And so that's kind of nice, right? Because now the only difference is that we're hypothesizing about the mu subscript d for the differences. But mu is equal to 0. Think about what it means for a difference to be 0. It's kind of easier to talk about our test 1 versus our test 2 scores, right? If the difference is 0 between those 2 scores, there was no improvement, but you also didn't do worse on test 2 than on test 1, right? So they're the same, right? Essentially the same. And so if there's no significant difference from 0 in the differences, that's where it gets tricky because we're talking about the differences being different from 0, then there's no change essentially. So what you'll notice for matched pairs is all I've done is I've tacked on a little subscript D everywhere, right? Mu subscript D, X bar subscript D, S subscript D, N subscript D. And your degrees of freedom, because you just have one sample of differences, you take your sample size of the differences minus 1 and minus 1. Oh, forgot to mention that. So here, I'll zoom in. Pop up. There. Should have scrolled down a little bit. Again, we do all our hypothesis testing assuming the null hypothesis is true. Right? And so if the null hypothesis for matched pairs is always that mu d equals 0, which it is, that's always the case, then we don't need to have minus mu d here, right? Because that's always going to be 0 because we assume the null hypothesis is true, right? And so on your formula sheet, I don't know if I have this one or, anyways, it's just X bar of the differences over the standard deviation of the differences. Because technically it's minus 0, but we don't need minus 0 on there. Let me just see what's going on here. I have the minus 0 on there, but. Oh, and on this formula sheet, I have X bar of the differences, so diff instead of D. You can use either or. Because as a department, we're migrating to a common formula sheet. That's what's on the common one, so that's what I figured I'd put on there. But it shouldn't be too bad to. D is diff is D. Okay. And then once you have your t that you've calculated, right, you can use the t table to find the p-value the same way that you did before, right? And then once you have your p-value, you can draw your conclusion the same way that we did before, right? So a lot of this is becoming more and more familiar, hopefully. Okay. Any questions about that? Okay. So I've got this example here. Zoom in. 200 observations were randomly sampled from a survey called High School and Beyond. The same students took a reading and writing test, and their scores are shown. I just showed them briefly over in the margin because it's not that important, but it's just to give you an idea of what the data looks like, right? And so we've got student number 1 has ID 70. So these two columns don't actually matter, right? This one's just telling you that you have a sample size of 200. Each student, of course, has its own student ID. That's fine. Okay. And then here is the score that they got on the reading, and here's the score that they got on the writing. And so because each student, right, might be, I'm assuming this is like an English test, so it might be strong in English or not as strong in English, right, or just maybe like me. It didn't matter how much effort I put into an essay, it was always 73%. Or if I didn't put any effort in at all, 73%. I'm just a 73% kind of writer, I guess. It's not great, but it's also not that bad. Well, it's not terrible. Anyways, probably a reason I didn't go into English as a major. So, and so for me, my reading and my writing scores are probably at the 73% level, right? And so, but if you're really strong, right, then probably both of those scores are going to be higher. So what we do is we say, well, because we've taken 2 measurements on the same student, right, then these observations or these 2 samples are not independent of each other, making them paired, right? They're paired on the student. Okay? So, oh, I guess I've typed these answers out. Oh, I've shown you the code on how to bring in the data if you wanted it. You have to install the OpenIntro package. And then you have to use the OpenIntro library. But then you can do, bring it in as .data frame just because it didn't import properly. But then if you just follow along there, you could be working with this data yourself if you wanted to. You don't have to, but just in case. So like I said, so this data is paired since we've made 2 observations on each student. So therefore, the reading and the writing scores of each student is not independent of each other. Are not independent of each other? Give up. So that would be part A. Essentially asking you, what type of question is this? What type of data do you have? We have paired data. Part B is not something that I'm expecting you to do, but I just wanted to show it to you just so you can see what it looks like. So compare the distributions of the 2 groups. At first glance, does there appear to be a difference between the average reading and writing test scores? And so here, to make a side-by-side box plot, we actually have to have all the numerical data in one column and then the categorical variable in another column. So I actually had to restructure the data a little bit. And I figured I'd show you how it's done because why not? Yeah. But you've seen side-by-side box plots in the lab, right? And so now when we're looking at something like this, and I got you to discuss it briefly, right, where you just have to say, well, it doesn't really look like, well, the medians aren't that different, right? The boxes are essentially in the same area. The only real difference is that the maximum didn't go quite as high. But overall, because there's this huge overlap, right, I already suspect that there's no difference in the reading and the writing scores, right, between the students. But we'll do our test just to see, okay? And so for your lab 6, which has been bumped to later now, right? When you set up your hypothesis, right? I asked you to make up a research question and test the hypothesis. Then what you can do is you can go back to your side-by-side box plot if you want and have a look at, well, what did it tell me? What do I think is going on there? Like I said, that's more of a side note, but helpful for the lab. So the side-by-side box plot does not indicate any major differences between the distributions of the reading and the writing scores. Okay. So what we do, we go back to the data here. To analyze these matched pairs, what we would do is we would make a new column of the differences. We can do reading minus writing. As long as we're consistent, you can do writing minus reading, right? But I always just do the first column minus the second column because it's easier for me to look at, right? And then I can find 57 minus 52. 44 minus 33. And I give up. Who does math anyways? Is 44 minus 33? Phew. Got worried for a sec. So you would calculate your differences. Now that you have this column of differences, you can ignore all of this information, right? You can ignore the individual reading and writing scores. Here's the thing though, you definitely can calculate the mean and the standard deviation of the reading scores. You can calculate the mean and the standard deviation of the writing scores, right? But also you can calculate the mean and the standard deviation of the differences. And once you've decided that you have matched pairs, then those are the values that you should be using. And so on the assignment, I think I've given you the mean and the standard deviation for all of these. Right? And so it's important to remember that, okay, if I have matched pairs, I don't actually care about that. That's just extra information. And I'm just going to focus on the mean and the standard deviation of the differences. Oh. Oh, are the assumptions for inference satisfied? Really went above and beyond on this one. So what I did, because there's 200 data points, right? I'm not going to do that by hand. So I calculated the differences, just took the reading minus the writing score. And then to make sure that the assumptions for inference are satisfied, the one thing that I will do is I'll just make a histogram of the differences. And as long as it looks approximately normal, which it does, right, then I can go ahead and say, well, then I can assume that it follows a normal distribution, and I'll use the t-test. Also, my sample size is large, right? My sample size is over 30. So then I can argue that even if it didn't look that normal, I can still use the t-distribution. Here's the blurb I stole from the textbook. They went really deep. Since the students are sampled randomly and are less than 10% of all high school students, blah, 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 blah. At the end of the day, even if these assumptions don't check out, we're still gonna go ahead and use the t-test because we don't have any other tools, right? And so that's why I don't really focus on the assumptions for t-tests, but I will for proportions. So then I calculated the mean and the standard deviation of the differences. And so now I have everything I need, because how many differences are there? There's 200 differences, right? Because there's only 200 students. And so even though they had 2 observations each, right, there's only 200 differences. And so I'll just add on here that n diff is 200. I'm guessing part D asked us to do the hypothesis. Let's see here. Do these data provide convincing evidence of a difference between the scores on the 2 exams? So here, if we just want to know if there's a difference between the scores, right? We're not hypothesizing about one being less than the other, right? We just want to know if they're not equal to each other, right? And so that's going to be the key word that you're looking for if you have a 2-sample or a 2-sided test. So, like I said, the null hypothesis, once you've decided you have paired data, is always H naught is that mu D equals 0, right? Which means that your alternative is also about mu D and how it relates to 0. And in this case, we just want to know if it's not equal to 0, right? Is there a difference between the 2 groups? We don't care which way. And then, because we have our mean of the differences and the standard deviation of the differences and the sample size of the differences, the t that we calculate looks really similar to the one that we just calculated, right, for 1 sample mean. And that's because we just have 1 sample of differences. So then when we go through and we do our calculations here, we find negative 0.867 as our t. That's not that surprising, right? Because just looking at our box plots, we said they look approximately the same, right? And so this is just confirming that, no, those mean scores or the mean difference is not that far from 0. Step 3, we're going to find the p-value. So again, using the t-table with 200 minus 1 degrees of freedom. Oh, I should have, it's a little copy-paste error. ND minus 1 is 199, but we know from our table there is no 199. So we're going to go to 100. And our calculated t was negative 0.89. Oh, that sounds too familiar. 0.867, right? And so we jot that down from step 2 in the middle here, middle of your page, the easiest way to go. Wrap it up in absolute value brackets, right? And that's what's saying we can ignore the negative. And then we write down the bounds that we find on our t-table, exact same thing that we did before. And that's what's nice. Once we have a t, those steps all stay the same, right? A t is a t is a t. No, it's just a t. So we have our calculated t, the absolute value of it is between 0.845 and 1.042. Is that right? Keep going back there to check, but I keep forgetting. Right, and so now we can scroll down to, now we have a two-sided test, right, because we wanted to show that they're just not equal to 0. And so our p-value is somewhere between 0.3 and 0.4. So I will make a note up here in our hypothesis that this is a two-sided test. And so our two-sided p-value is between 0.3 and 0.4. Okay. Got a little blurb here, right? Because if we think about the p-value, the definition of the p-value is the probability of seeing something as extreme or more extreme than what you saw, assuming that the null hypothesis is true, right? And so technically, the p-value is the probability of obtaining a random sample of 200 students where the average difference between the two is at least 0.545, which was the sample mean. If in fact the true average difference between the scores is 0, right? So if the null hypothesis is true where the difference is 0, what's the probability of seeing a difference of 0.545? Well, that's the p-value. So now we can state our conclusion, same format as before, right? Since our two-sided p-value is between 0.3 and 0.4, both of those are really high, right? It is not less than the assumed alpha level of 0.05, which means we do not have enough evidence to reject H naught. Just as we suspected all along, but now we've got confirmation here. So this means data do not provide convincing evidence of a difference between the scores on the two exams, and I've just reworded the question as an answer. Any questions about that one? Okay. So then the final part on here. Oh goodness. Suppose we were to construct a 95% confidence interval for the average difference between the reading and writing scores. What would you expect, would you expect this interval to include 0? Yes, right? Because we just decided that we can't reject the null hypothesis. The null hypothesis says that, well, the mean difference is not significantly different from 0. And so if we made a confidence interval, right, 0 should be in that interval, right? Because it's kind of the reverse of using a confidence interval to do a hypothesis test, right? If your interval is not on the hypothesized mean, then you can reject the null hypothesis. If your interval is on the hypothesized mean, right, so your hypothesized mean is somewhere in there, then you can't reject the null hypothesis, or you don't have enough evidence to reject the null hypothesis. So kind of reverse engineering, we can say that, okay, well, if we're not rejecting the null hypothesis, then 0 must be in the interval, right? Or it would be in the interval. So even though we're not making the confidence interval, although you definitely could, we still know that 0 would be in this interval. Okay. Here's how you would do this t-test in R, if you wanted to. See if you have any side notes. Nope. The only difference is you have to have your first sample, your second sample, and then just tell it that paired equals true, and then you can just use the t.test command, and it calculates our t, it calculates our p-value 0.3868. We could only say that it's between 0.3 and 0.4. 0.3868 is between 0.3 and 0.4. Fair enough. And here we have our confidence interval, right? The one thing that R is a little bit picky about is if you need a confidence interval, you have to have a two-sided test, which is the default, right? I haven't specified. And so to get the full interval, you have to have a two-sided test. But between negative 1.78 and positive 0.69, 0, because I go from negative to positive, 0 is in there, right? Just as we suspected. Any questions about that? Okay. Let's see here. I know it's early. Okay. Let's start this one. I probably won't finish it. I like this one because it's funny to read. So this is the one where we're going to work through it together. And so insurance adjusters are concerned about the high estimates they're receiving from Jocko's Garage. Sounds like bad news. To see if the estimates are unreasonably high, each of 10 damaged cars was taken to Jocko's and to a trusted garage, right? So they have a garage that they trust their estimates, right? And then they're going to compare those estimates to Jocko's estimates. So they've got 10 cars, right? We know that not all cars are going to have the same amount of damage, right? And that's going to affect what the estimate is. Right? And so if there's a lot of damage, then of course both garages are going to give a high estimate, right? But what we do with paired data, because we're doing these two measurements on the same car, right? We just calculate the difference between the two, and then we'll be able to see, to analyze the differences between the Jocko's estimate and the trusted estimate. And so as we can see, right, for the first car, Jocko's estimate's 500, and the trusted garage is estimating 430, and then 1550, 1500. Here, Jocko's estimate is actually a little bit lower than the trusted garage, right? And so we go through, and to analyze these, we would have to calculate a column of differences. So is there evidence that Jocko's estimates are significantly higher than the estimates from the trusted garage? If we want a one-sided test for paired data, it's actually a little bit trickier than for just one sample, right? Because we want to know, okay, well, our hypothesis is about the difference, right? The mean of the differences, and how does it relate to zero? And so what we need to know is, well, if it's higher, what does that mean in terms of the mean difference to zero, right? And so we'll kind of mungle that. But first, we'll go through. And notice that below here, I've got the mean and the standard deviation of Jocko's estimates and the trusted estimates. But what we're going to be doing is we're going to find a column of the differences. First, I'll answer if this is paired data. Yes, right? Since each car is having or is getting two estimates, right? Or since we have two estimates for each car. Right. Two observations on each individual or subject is paired data. So if we want to calculate the differences, Jocko minus the trusted garage, 500 minus 430, 70, 50, negative 50. Just to make sure. I'm going to cheat. I'll stop there. You can go through and calculate it, right? And then, just for practice later, you can find the mean and the standard deviation of the differences. This is really just to bring home that in the end, we're just going to be looking at these differences and we're just going to analyze these differences, right? And so that's what you would have to do. But if you read along here, I've told you the X bar of the differences is 80 and S of the differences is 84.59052. So you can definitely go through and check your work. But what you'll find here is that the mean is 80 and the standard deviation is 84.59052. One thing that people get kind of hung up on is that 550, I'm just talking about this guy here, because the standard deviations, how we calculate those, remember there's a square root in there, and so that's going to bungle things up. But here, if we did 550 minus 521, you're not going to find that that's the same standard deviation. And that's just because the standard deviations don't work that way, right? And so we have to go through and we have to calculate the standard deviation, or more likely, I have to give you the standard deviation of the differences. Right? And so they don't behave the same way, but 550.25651 minus 521.113551 is 29.121, which is not 84.59, right? It's just not. So I guess I'll start C here. Your null hypothesis, we've already decided that this is paired data. So we already know that our null hypothesis is that mu D equals 0. HA has to be about mu D and how it relates to 0. And we wanted to know if Jocko's estimates are significantly higher than the trusted garage. One thing that you could do is, okay, if Jocko's estimates are higher than the trusted garage, you could just look at how you calculated the differences, right? If this is higher, always higher than this one, then we would get a positive difference. Sometimes that's hard to kind of wrap your head around, right? And so what I would do is I would just look at one example where, okay, well here, I've got an estimate that Jocko has a higher estimate than the trusted garage, and the difference is positive, right? And so it's greater than 0. And so that's how we're gonna go, because we have to hypothesize about how the mean of the differences relates to 0, right? And so since, actually I'm gonna use a different color here. Since the difference is Jocko's minus trusted, if Jocko's is greater than trusted, we can say J minus T is No, I didn't want to do that. Too much notation. Then the difference must be positive. So the difference must be greater than 0. Which makes our alternative hypothesis that mu D is greater than 0. So we have a one-sided test. So for one-sided tests for paired data, it requires a little bit more thought put into it, right? How does the sign relate to 0? But once you have it, then the calculations are all the same, right? All right. I think we'll end there for today, and then we'll pick it up next day. Any questions though before? No? All right. Oh yeah, if you didn't get assignment 5, come grab it here. And see you guys on Monday. Yes.